Total internal reflection is a most important effect in optical technologies. Optical fibers, lasers, waveguides, signal processing circuits are all important to modern communications. Total internal reflection is essential to these technologies. Consider a wave incident from a medium to another. In particular, it will be from a high refractive index medium to a lower one. Start out with a small or moderate incident angle. The transmission wave can be determined with a geometric perspective by first, drawing a semicircle of all possible k-vectors. There is only one position on the k-circle, that is only one transmission angle that meets the condition of field continuity at the boundary, determined by beta k component along the interface. The other k component, k2, is determined by the Pythagorean theorem as shown. There is a uniquely determined transmission wave into the second medium, carrying a portion of incident wave power away from the interface. The angle satisfies Snell's law. If the first medium has a higher refractive index than that of the second, as the incident angle increases, there is a condition in which the Pythagorean geometric model becomes uncommon for conventional geometry. Since beta k component is even larger than the capital K2 semicircle radius, the other component, K2, cannot be real, but imaginary. This is represented by a straight segment without an arrowhead. The electromagnetic field in the second medium goes through a categorical change of property as the K2 component makes the transition from real to imaginary. For the latter, the EM field is known as evanescent, characterized by an exponential attenuation versus distance from the interface. It is also known as near field, to indicate its limited spatial extent, as the opposite to far field, which applies to radiating field that theoretically extends to infinity. A key property of evanescent field is that it travels only along the boundary, not into the medium. Hence the wave does not take or carry power from the incident wave into the second medium. The implication is that the incident power is completely reflected, hence this is known as total internal reflection. This illustrates the process from transmission radiating wave to evanescent wave as a function of the incident angle. The angle at which the transition occurs is known as the critical angle. Besides amplitude, phase is also important in total internal reflection. The phase of a wave can be observed along its axis of propagation. This is shown with a plane drawn as a cross-section of the incident wave planar phase fronts. A similar axis is drawn for the reflection wave. Both are joined at a reference point on the interface, where their relative phase can be compared. For the ease of visualization, the incident wave needs not be graphically rendered, and its propagation axis can be folded over for straight joining with the reflection wave axis. For the present case of transverse electric polarization, and radiating transmission, not total internal reflection, from a high refractive index medium to a lower one, the reflection phase is the same, that is zero phase angle, with respect to the incident. below the critical angle for total internal reflection, but above the Brewster's angle, both TETM reflectivities are real and less than 1. They have opposite phases. Above the critical angle for total internal reflection, the TETM reflectivity magnitudes become 1, and complex with non-trivial phases. Unlike metals, the E field in the second dielectric medium cannot be abruptly zero at the interface, hence since the reflectivity magnitude is 1, there is necessarily a non-trivial phase for non-vanishing evanescent wave. The reflection coefficients are ratios of two conjugate quantities. Hence, each term argument is twice of that of the term, either k1 minus I kappa 2, or ik2 epsilon 1 minus k1 epsilon 2. Their phase difference is of particular interest for some applications. Numerous approaches use the difference of TETM total internal reflection phases to control a light wave polarization. A common one is the Fresnel-Rom, designed to give a quarter wave phase shift. It can convert a linear polarized light to circular and vice versa. The chart shows a plot of the phase of the reflection coefficient as a function of incident angle. The top part, blue-purplish, shows the phase of TM reflection. The bottom part, orange-red, shows the phase of TE reflection. Their difference is shown with the magenta color curve. If the refractive index of the ROM is above approximately 1.5, there are always two incident angles for which the TETM phase difference is 3/4 of pi, which is 3/8 of a full wave. However, it is not most convenient because these exact values of incident angles must be used for the desired phase shift. Around n equals 1.5, the minimum of the phase difference is right around 3/4 pi. Because it is a minimum, the angle of incident can deviate from the exact value with only a quadratic error. It is therefore more tolerant to the angle cut and polishing error in the manufacturing of the ROM, as well as optical misalignment in usage. For TE total internal reflection, the transverse E field is continuous, and the field lines of H field consist of loops that are smoothly continuous at the interface. They are smooth because both tangential and normal H field components are continuous, as virtually most dielectric media have the same magnetic permeability at optical frequency. For transverse magnetic, however, while the transverse H field is continuous, it is not smooth, as the field gradient, that is the derivative, along the normal direction is not continuous. The electric field loops display break at the interface. A close-up view of the E field lines shows the line tangential break more clearly at the interface. Or the E normal component can be directly plotted in 3D to show the discontinuity. The continuity of normal D displacement field, and difference between the two dielectric constants necessitates the E normal component discontinuity. For the same boundary condition reason, while H transverse is continuous, its derivative is not at the interface. The Goose Hansen shift illustrates a fundamental difference between the total reflection from a perfect metal mirror, that is, a metal with infinite conductivity at the optical frequency, versus dielectric total internal reflection. Consider a beam, such as a Gaussian beam incident on a perfect metal mirror. Its beam center is on the interface. The reflected beam has exactly the same beam center and beam waist, just a change of the direction and a minus sign, or a pi phase shift for the E field. For dielectric total internal reflection, because of an angular dependent phase shift, that is, a spatial K-dispersion, the reflected beam is slightly distorted. However, for up to second-order approximation, the reflected beam remains Gaussian, except that its beam waist is not at the same incident beam waist location like that of a perfect metal mirror, but is shifted laterally and longitudinally, which are proportional to the first-order and second-order derivatives, respectively, of the reflection phase versus K component. The gamma expression on the graph is proportional to the first-order derivative of the phase of the TE reflection coefficient, and is an approximation of the lateral shift of the reflected beam axis as indicated by the blue double head arrow. It is as if the beam was skipping or sliding by penetrating into the second medium over a distance on the order of its evanescent exponential depth, before being reflected back. It will be seen that the Goose Hansen shift is a part of typical dielectric waveguide behaviors, as an optical field with evanescent wing penetrating deeper into the cladding region with lower refractive indices, will skip and slide faster than a field that is more confined to the high-index core region. This will be seen in the sneak preview of Chapter 5 next. Consider a 5-layer semiconductor planar structure with a refractive index profile as shown. The two outermost layers, left and right, are so thick that they can be considered as semi-infinite. For a beam of light sent into the structure, to be propagated along and confined in the layers, not going across them, there are only a finite possible waveforms, referred to as modes, that it can take. For a wavelength of 1.5 micron, there are only 6 modes if the polarization is transverse electric, and 5 modes if transverse magnetic. Any light wave to be confined in these layers must be a linear combinations of these finite number of modes. They have one thing in common with each other, and that is all have total internal reflection evanescent waves in the left and right outermost layers, known as the claddings. As a rule of thumb, the more spreading out a mode, the faster it travels. One can think that these modes have different quote-unquote Goose Hansen shifts on the two claddings, and the modes that penetrate more into the claddings for skipping and sliding, travel faster than the ones that stay closer to the inside layers, also known as cores. If a light wave is in purely one of the modes, not mixed, then at a cross-section, or the edge of the layers, the light intensity will look like these profiles, which are simply proportional to E field square as indicated. An edge-emitting diode laser typically has its light generated inside a structure like this, traveling to the edge and escapes to be used. In practice, for application performance, it is often most desirable to use structures with only one mode, known as single-mode waveguides. Hence, typical edge-emitting diode lasers have an intensity profile that looks like the mode labeled 0. Similar to the previous, these are the profiles for TM modes. This wraps up by showing the evanescent waves in the claddings of two particular modes. This is the most important application of the total internal reflection effect.